And we are ready to go.
Hello, can I?
Yeah. So today, before we start the meeting, I would request Professor Sheshadri to share a few thoughts that are on the top of all our minds.
Friends, today is a sad day, especially for astrophysics. One of the very eminent astrophysicists, T. Padmanabhan, is not with us anymore. He passed away today morning. It was very sudden. And I know Padmanabhan very well because I was his first student from 83 to 89. And my relation with Padmanabhan had been very informal. It was more of a friend than a guide. And in fact, I became a student in a very interesting way that we were just discussing what am I supposed to do, what I will be doing in PhD. And suddenly it occurred to us that since he's in the faculty, he can be my guide, and then that's the way it happened. He has been very prolific, and he's a person who is a very good researcher as well as a very good teacher. That is one very great thing about him. And he has worked, there is other thing which was very great about him was that he inculcated the feeling that, when you are interested in physics, you are interested in physics as a whole. I mean, one doesn't get compartmentalized. And and he himself had a very breadth of interest, right from history to religion to physics, etc. And he has written a number of very good books, and which are being followed at several places in the world. And yeah, I do not know what else to say. He is survived by his wife and daughter. And I just pray God that he give them strength to bear the loss.
Thank you, Sesh. I know it must be really difficult for you at this moment. Devika and Sampurna, would you like to take over?
Yes, sir.
Yeah, Devika, you continue.
Yogesh, you can go ahead with the introduction.
Yes. Actually, it's sad for us to lose such a knowledgeable person. Like he had many PhD students under him, and he had born with an aim to get every prize and designations. Like he had written 13 books, and it's a sad thing for India to lose Padmashri Padmanabhan. And myself, Yogesh Kumar, is actually feeling privileged to introduce today's seminar's host. Actually, like I first extend my warm welcome to all. And in saying warm, everyone does not like warm in all the times, because doing summer it will be like scorching heat. But with his knowledge, Professor Ninan, he had developed distinguished algorithms using machine learning and artificial intelligence, and predicted a rainfall pattern. And also, he had done an experiment on wet summer. It is long-term rainfall, and he does not have just only software skills. He's excelled in hardware also. Like he had set up a 16-node cluster computer in India, and that too. He's been like he developed a own Linux OS, Atma, ATMA, which the motto of being a lightweight Linux distro, easy to research and analysis. It can be deployed anywhere without any installation. And he thinks it's time to patent opportunity. So he lives by the GNU community that there should be no property software, and his knowledge is open to all. And also he has many. He got many awards, and the important one is he finished his BSc in Kerala University, and then MSc in Mahatma Gandhi University, and PhD in Cochin University of Science and Technology. And he has been a member of IUCAA, International University Center for Astronomy and Astrophysics. And he has been a member of 3 professional bodies, which is a Virtual Observatory, India, and International Virtual Observatory Alliance, and Astrostatistics and Astroinformatics Portal, and then the International Statistics Institute. His while we are thinking on his research on many things, he developed a technique on studying interactions on brain using EEG under influence of alcohol and sedation state. And then he has not restricted his delivery of knowledge just in India, and he has gone abroad to many countries such as the United States and from across Europe, like UK, Swiss, and many. And he's the author of a data mining software named DBNN. That is widely used in astrology and other data intensive areas. And he has exploited in a good manner the uses and advantages of machine learning, artificial intelligence, neural networks. Like when the world applies to science, and here we have a man who applied in their life and benefited many. And he has like more than 10 journals printed, and some of them won awards actually. And also here he has been main part of many conferences and written books, like that too, also more than 10. And he's not just a man of knowledge, but also a man of values. And I'm very privileged and happy to introduce Dr. Ninan Sajeeth Philip to teach a seminar in our Astronomy Club of CUTM. Welcome, sir.
Thank you, Yogesh, for the introduction. Today, as Sesh was mentioning, is a day of great loss for India. We have lost one of the most eminent personalities we had, and paying homage to him. Let's start the meeting. Shall I share my slides?
Yes, sure.
You're a co-host, so you can start directly.
Yeah. So this is a picture of Padma Shri Thanu Padmanabhan that appeared in this week's regional magazine. He was giving a interview with them, and most of us were reading this article when the news came that he just passed away. So it's a great loss, and we are really saddened by this news. But let's move on. So a warm good evening to all of you. Seeing my title screen, I'm sure that many of you might have desired that it would have been much better if the letters were clearer and the frames had a fewer number of stars. In fact, that is a prayer and desire of every astronomer. The star cluster is a real image taken by the Hubble Space Telescope. Just as you thought, it is very hard to study and understand how these trillions of stars just happen to be surrounding all of us and burning ever since history had begun. It is people like you who have chosen to study and explore the cosmos that should demystify this complexity and puzzle that surrounds us. So relax and listen to what I have to tell you for the next 90 minutes or so. By the way, is my screen visible to all of you?
Yes.
Yeah.
Yes, okay, great. Now, this is one of the oldest monuments we have. It is supposed to have come from Mesopotamia and has Babylonian origin. It has carvings which shows the sun, moon, water, and even some writings in the Urdu language. And this is at the Archaeological Museum of Iran. In fact, dating back to 1800 BC, or even before, the Babylonians were among the first civilization to document the movements of the sun and the moon. They maintained a very detailed record of the motion of these celestial bodies, taking daily, monthly, yearly records of the movement of the planets and stars, including Jupiter, for example. Of course, all this information was assigned mystical value, used to warn the king about possible catastrophic events. It is said that the first appearance of the famous Halley's Comet were documented by the Babylonians. And it is also them who first divided the sky into different zones to mark positions of the celestial objects in the sky. Greek scholar Eratosthenes, who lived from 276 BC to 94 BC, had excelled not only in the field of astronomy alone, but in geometry, mathematics, poetry, and music as well. He is well known for several astronomical breakthroughs. His most important contribution, as astronomers point out, is the calculation or the estimation of Earth's circumference. His computation was off only by a few hundred to few thousand miles. It is closely accurate considering the lack of apt technology during that time. He is also responsible for calculating it is believed that he was able to calculate precisely the tilt of Earth about its axis when it goes around the sun, which is responsible for the seasons we have, and also for the estimation of the need for a leap year or leap day. Greeks were very good contributors to astronomy and mathematics. Pythagoras, for example, is another Greek philosopher. who is better known for his contributions to mathematics, but also have contributed to astronomy. Pythagoras postulated that, like other celestial bodies, the Earth is also spherical in shape. He came up with the idea that when he noticed that ships that when they sail disappear when they pass the horizon and reappear when they return, which according to him was possible only if there is a curvature. He was the first to suggest that the movement of the planets, sun, moon, stars, all could be equated in numbers. So these are the historic great leaders we had in astronomy. And of course, in India also, Aryabhatta, who has made very precise calculation of the movements of the planets. Although his works were under the premise that the world is geocentric, many of his calculations are still of great value to modern mathematics and also to astronomy. Aryabhatta, for example, was able to assume that the Earth is rotating on its own axis, going around on its own axis, and that the moon and the planets shine through reflected light that is coming from the sun. Well, the list is endless if I go on to enumerate them. The major difference between the past and the present is not just in the intellectual development that we claim to have. It is mostly the instrumental capability we have. We should remember that all these great giants of the past did not have a telescope or even a calculator to make these remarkable observations. That is what makes them stand out as heroes. Now, how did they achieve, or how do we do astronomy? One of the key requirements for doing astronomy in depth is the archives that we have. Since astronomers do not have the freedom to set their lab as they wish at a place where they have the facility, they are dependent on data. And where does this data come from? This data arrives from the skies and from the trillions of celestial bodies that decorate our night skies. Thus, until recently, very recently, when bioscientists started studying the human protein and genome, astronomers were way ahead of other branches of science in achieving data, in archiving data, and analyzing and systematically doing it with highest precision to understand the universe we live. This led to the practice of gathering data and storing them on writable, of course, in the olden days, on stone tablets, leather, paper, etc., mostly in the forms of drawings and mathematical formula. But the important thing I want to share is that the practice is still continued. For example, the European Southern Observatory, ESO, has thousands of gigabytes of data that are archived every day. Though collected and archived through a huge funding from public money, astronomers also have the practice of freely distributing this data to the world community, the research community, the student community, to analyze and publish. They only insist that they should acknowledge for the data they provide, and it should not be used for any commercial purpose to make money, because it is knowledge that is supposed to generate profit, not money. I would recommend all of you who are interested in astronomy to look at archive.eso.org to find a lot of data that is available through the services. It would be a good price to start. Now, moving forward, there is also Simbad, which is a very big database. In fact, it is more than a catalog. It's a catalog based system, but it's more than a catalog, where you have almost everything. As you can see here, They provide identifiers, coordinates. They allow you to have access to journals which have been published on different topics that are in astronomy. All these things at one place. So they provide user guide, they provide presentations, they provide training material. So this is also another site I would like you to go and take a visit. In fact, we will be returning to the site later in the talk. Why we need this kind of data? To give you an example, there are stars in the sky that appear to move with respect to the other stars in the sky. Because we ourselves are moving, we can compare it only with other stars in the sky. And this is called proper motion. Though these stars move related to other stars, due to the very far distance from us, just like an aeroplane flying at some 700 kilometers per hour appears to be moving slowly through the sky, the displacement of the stars with respect to us, the angular displacement is very small that it is impossible to visually see their movement. So we can see that movement only if we plot their path for several years. Then we'll see small variation in the positions. So these kind of stars can be discovered only if we have archived historical data which we can process. Similarly, there are stars which change their brightness with respect to time. Such stars are called variable stars, and there are different types of variable stars. And in fact, it is these variable stars that enable Hubble to discover that the universe is expanding. So you see, all these things, these variations cannot be seen in real time. You do not see them varying in real time. Of course, some of them may twinkle, but that is because of the atmosphere, not because of the variation that we are talking about. So these things are very crucial in our understanding of the universe and are also can be obtained only if we archive data. So archiving data is one of the primary prerequisites for doing astronomy science. And these services are in fact very good in doing that. I'll just demonstrate how easy it is to do that. SIMBA provides a highly interactive query field which has catalogs, and you can just query what you want from them. So you can query based on the different wavelengths that you are interested to look at the object at, because everything is electromagnetic. We are coming to the era of this multi-messenger astronomy where we will hope to have gravitational waves also, another arm for us to understand the universe. But as of now, we don't have sufficient knowledge in gravity, and we are trying to understand it, how it can be used for doing analysis. And by that time, we will be able to do more of gravitational related observations. We have already started doing it and finding optical counterparts for many of the gravitational wave sources are being one of the most challenging research areas that are going on. Now, when you are talking about the electromagnetic spectra, it has to be divided into various bands and looked into in depth through different types of telescopes. For example, radio cannot be observed using a lens. You need radio antennas to receive that, although it is electromagnetic. Similarly, optical means the visual band, the IR infrared band, then the ultraviolet band, and X-ray, for example. All these things require different types of telescopes. And as a result, we have divided them into different bands of wavelengths, which can be observed. And depending upon the bands in which they are observed, you'll need different technology. And all these bands of observations on the same object can be obtained through this SIMBA service. That is one advantage. If you want in the observation, all the bands, you can just leave this blank. Or if you want to have it in one particular band, you can select that band and get it done. Similarly, mission-based observations are also possible, where you have different missions. Missions means different survey programs, maybe based on space surveys or maybe ground-based surveys that also based on surveys also you can make. I'm sorry, am I? Hello?
Yeah.
It seems I have lost my connection, or
I can still hear you and see the first page. Paying homage to.
okay, okay. I think something happened. I'll just come back to you. Just a minute. Let me move on. I do not know what happened. Is the screen visible now?
It is.
Okay. All right. Yeah. So based on mission and based on different objects of interest, like AGNs or whatever kind of objects you are interested, that also is possible. And you can just specify what object you are interested in, and that will be that can be even you can search by author's name. You can search by author's name, keywords, or title or description of the data, whatever you are interested in, and that will be displayed. And in this particular case, you have about 21,000 different catalogs that are available, which can be used. For example, suppose I'm interested in studying about variable stars, of which I mentioned before. Then all I need to do is to type variable star there and click the find button. And as I said before, I can select also these different bands or different missions or different astronomical. And when I do that, this is something I get. So I find that there are about 1,725 matching catalogs that describe variable stars. So that will use the size. And in that, I'll see different fields. And these are, in fact, these are the references to different publications that have come up on those topics. And these are links to the particular data set. And you also find here a box in which the ratings of the particular objects have been given. So you find that here, Gaia is here. Gaia has the highest hit or maximum number of people have been looking for Gaia. So that is what you mean by these numbers here. Number of people who are looking for this particular data. So that is available, and that is shown in these boxes. And you can even click on this box to see the daily demand or the monthly demand in whatever way you want for the data that has been demanded from this particular site. Likewise, there is also this references that are available, all these journals, and you can click on them, any of them, and you can get the corresponding data. So you find that in the particular paper, there are periodic variable stars. There are about 50 rows, meaning that there are 50 different stars which have been found to be periodically variable in this catalog. Then there are periodic stars, candidate periodic stars, which means that they are periodic, but we do not know what type of periodic stars they are. There are about 146 of them. Then there are non-periodic variable stars, which may be just appearing randomly periodic. They are non-periodic, meaning that they may happen only at once or they may happen randomly. Some stars behave like that. And there are 1,019 of them. And each of these objects you can take, you can see their image. For example, here they have given the sky fruit. So if you click there, you will be able to see them. And this is in fact showing the details about the catalog. So you can find out, you can select whatever entry that you are interested in. If you are interested in knowing the locations are at positions which represents the sky coordinates, you can have them, right ascension, declination, you can have them. Their period, you can get that, their magnitudes, everything, different magnitudes, I magnitude, indexes, color indexes, and V magnitude, different magnitudes you can obtain. All these things are available. And what happened? I do not know. Occasionally it goes on. No idea why. Okay. As I mentioned, this region shows the region from where this catalog has been taken. So you have the details about the catalog based on your selection. You can start Aladdin, for example, which will be able to display the particular frame. So you can see the image that you have been looking at, and you can zoom in, zoom out, and also do all those things. You can plot the output. You can get the plot of the output. Here it is plotting the I magnitude and the V minus I index, which is the color index that usually astronomers use to represent the particular type of star, because each star can be considered as a black body, and their emission can be represented by the Planck's black body emission, and V minus I will represent a particular kind of star. It can be used as an index to represent a particular kind of star. So that index is what is mentioned here. But you can, of course, change this to any value that you want from the catalog by just pressing this button. So these are just details. I am just going through them. Very useful tutorials on all these things are available on the web, and you can go through them. My purpose is only to introduce you to some of them, because we want to do something using these techniques. Of course, if you're familiar with SQL queries, you can write SQL queries also and get data from them. Now, when we started archiving data, one of the greatest challenges was to make it available to the people. See, it's very easy to archive data, keep it in my shelf. But if I want people to use it, it should be made available to people. So this is what exactly the Virtual Observatory has been trying to do for several years now. What it does is it makes all these catalogs available to the public through a web service. And making it available through web service, these are huge databases, terabytes of database. So it's making it available to the public through websites is a highly challenging and cutting edge technology required application. So Virtual Observatory is trying to do exactly that. And Skyview is one of the initial Virtual Observatory services that I would like you to look at again. Because this is a practical talk, I want you to have a look at all these different services that are available. Although it might look boring to listen to this kind of a talk, I think this is what you need to have at least some knowledge of to start with astronomy. So what Skyview does is it again allows you to do searches. You can specify whatever objects that you are interested in. For example, if I am interested in the major object 87, which is an interesting galaxy, I can just type M87 here and select the survey that I want. DSS is the Detailed Sky Survey, digitized version of the photographic images. And if I click go, then what happens is that it takes me directly to that particular object. So it shows me the object. This is a digitized version of the photographed image. So I can see that I can zoom in and zoom out, but there isn't much to be seen here. But I can change the band. I can change the band and go to other bands and look at the object. For example, if I go to the radio, then instead of the galaxy that was supposed to be here, I see a spot here. And if I zoom in, what I see is that it is not just a spot, it is a jet, a stream of jet that is coming out of it. So what is a stream? This is, see, it's in the radio, it's in the radio band. And if I see something like that, it should be associated with some very active movement in the center of the galaxy. And definitely that's a black hole. And what happens is that when the black hole accrete matter, it's causing the matter to move at very high velocities and also create a lot of heating effect in the time, causing to emit energy in X-ray and all other bands. And at the same time, because they are charged particles they are ionized and are charged particles, they have magnetic field, and this movement will cause streams of synchrotron emissions to happen. And that is what you are seeing. So see, when Hubble Space Telescope was able to take a very beautiful picture of this center of the galaxy, it was able to see this whole jet coming out through several megaparseconds in the sky. So this is a kind of facility that becomes available at your fingertips on your desktop when you have virtual observatory observations available. So that is what we are. That is what virtual observatory is trying to bring in, and that is why it is important to know. Now, if you look at the same object in X-ray, you can see very clearly those jets that are coming out. And identifying the location of the black hole is really a tough thing. And recently, there has been a publication. Recently means a few years back, there has been a publication in which they use all these different observations to find out the location of the central black hole position. So you see that it's not sufficient to have one observation. It is not sufficient to have a set of observations in a particular band. It is also important to have all these records, all these collections of information to do real scientific research in these days. As I mentioned, this is a technology-driven, this is a data-driven world that we are living in right now. We are not in a world where some of the great giants live. Those were the days in which your intellectual capacity was most important. These are the days in which your technological capability also adds to your intellectual outcome. Okay, now I want to show you some of the applications as I mentioned. And in Virtual Observatory, there are at least two important applications that you should not miss out. And one is Aladdin and other is Topcat. I'll come to that later. It can be used from an introductory research level and can be used at research level also, because it is so versatile and so powerful that it can be used. Now, if you are using Linux platform, especially Ubuntu platform, you can just apt get this Aladdin to your computer. Just type in sudo apt install Aladdin and it will install Aladdin on your computer. It's a Java-based system and it's very powerful in just spanning, in just bringing the digital sky on your computer. So this is one application I would suggest that you should not miss. Now, this is a default screen when Aladdin opens. As you can see on the left side, on the top here, it is already linked to several catalogs in Simba, so that you can directly go and get fetch for images from them. This makes it extremely easy for astronomers to search, find, and work with real images of desired objects. Suppose I am interested in studying about Andromeda Galaxy, which is our nearest neighbor, which is called the Measure Objects 31, M31. I can type in M31 in this command window and click Enter key so that it will take me to the Aladdin. It will take me to the M31. It will take some time for the display to come because it has to search and get the image and get me the screen, corresponding screen. So Aladdin has, I typed M31, Aladdin has in fact found out the coordinate of this particular object and brought me the screen of the Andromeda Galaxy. And although this is a JPEG image, it is linked to all the database, which means that it is as good as a real fixed image or whatever format in which you are storing the image. So that is the important point I want to make.
In fact, I think we can say that it is all the observatories at our fingertips at the same time.
Absolutely. That's it. Yeah. Thank you, sir. Yeah. Okay. The default image that is displayed is from the DSS, which is the Detailed Sky Survey, of which I mentioned before. And I can, in fact, change this. There is on top, you can see all these different options. I can go to different surveys. For example, PanSTARRS is one of the latest surveys, and I can get very precise, very high resolution images of this particular galaxy just by selecting PanSTARRS. So if I select PanSTARRS, you can see that the whole blurred image has been resolved into stars here, and it's it looks different from the previous image for two reasons. In fact, it is not just because of the resolution alone. First of all, pan-STARRS is looking at the sky in a different band of the electromagnetic spectrum. Just like the color and the detail of your shot will change depending upon the color of the light in your room. When viewed in different bands, the same object might look different. That's one reason. The second reason, of course, is the resolution of the image. The resolution offered by the pan-STARRS is much better than the DSS. Thus, you can see the background stars and also the background galaxies, nearby satellite galaxies that are there. So, this is the great advantage you have to think of. And it is possible to navigate through each of these surveys to see how the same objects looks in different surveys. That is the main advantage. You can see how it looks, just like the doctor would like to take your X-ray to see whether you have a broken hand or not. It's through a different band. You can look at the same object in different bands and you can see different details. You can see different depths of the particular object that you are looking at. So I leave it as an exercise for you to explore Aladdin, but I'll also give you a few examples just to give you the feeling that it is easy to do it. Now, what you see here is a set of objects that have been collected from Simbad that is being linked to Aladdin. And you can see all these boxes. Each of them is connected to Simbad. So this is one advantage that I have when I use this kind of tool. I'll show you another example where we'll go to the detail on how this is to be done. For example, suppose I am, this is now linked to Simbad, which means that each of this object that you see here is in fact having a paper attached to it, having somebody who has worked on it. And you can get access to what they found there, what kind of object they are looking at, etc. Now, suppose I am interested in this particular region, which is a galaxy, which is a satellite galaxy that I have here, which is the M110, I think. That's the number which corresponds to this galaxy. And suppose I want to zoom into this position. When I zoom into this position, I see that there are more number of boxes that are coming in, which means that although you see fewer number of boxes here, that does not mean that people have not studied all these things. This is just for the convenience of the display. Otherwise, this will fill this orange color boxes will fill the entire screen and you won't be able to see anything. So that is the reason why they have reduced the number of boxes that are shown. So this 3-4 boxes here has been resolved into this many boxes, and go to each of these boxes and you will be linked to the particular object that is there. Now, these are two objects that are at the bottom of the galaxy. On them and select them, and you find that it is one of them is a symbiotic star. Symbiotic star means it's a binary star. It's a binary star with a white dwarf and also a red giant near it. So this is a possible candidate for a supernova, type 1 supernova explosion. But it is known that not all type 1 supernova are caused by this kind of combinations, but some of them, at least some 20% or less than that, type 1 supernova is associated with a white dwarf and a red giant that goes around in symbiotic relationship. Okay, now, okay, this is the other tool, the second tool that I wanted to introduce to you, which is the Topcat. Topcat is also a very powerful table manipulation software, which is produced by the Virtual Observatory. And the advantage here is that it is linked both to Simbad and also to your local machine, so that if you have made some observation, you can use this Topcat to display that, to do statistic analysis on that, and a lot of things. So let us have a look at Topcat also. You can install Topcat again by the apt install command in Ubuntu. Just say sudo apt install Topcat, and that will install Topcat on it. Let us consider an example to understand how these two can be used together. I give this also just to make you familiar with the techniques that are available. So suppose I want to find out the distance to an Andromeda galaxy. Andromeda galaxy is our nearest galaxy neighbor. So we will use both Topcat and Aladdin to find the distance to this particular galaxy. So for that, we will be using the traditional method that was used by Hubble to show that the universe is expanding. And that was by using a particular kind of variable stars called the Cepheid variables. So Cepheid variables are some 4 to 20 times massive than our sun. So they are huge stars. And they are about 100,000 times luminous than the sun, which means they are very bright. And as a reason, they are classified, spectroscopically classified as supergiants in the class F62K2. These are the different classifications that astronomers use for classifying stars. And the important feature of this type of star is that the radius keeps on changing, and they change by millions of kilometers in each cycle. So when the radius becomes larger, their brightness, the surface area increases. When the radius becomes shorter, the internal pressure increases, and it keep on oscillating like this for years together. And the important finding about this Cepheid variable was made by one of the greatest astronomers who is less known. Her name is Henrietta Swan Leavitt. And Miss Leavitt is to be acknowledged for all the contributions, the great contributions that Hubble could make. Einstein, for example, had to take away his cosmological constant just because of the finding that Hubble made, which was based on what this beautiful lady found out through her hard work on data. In fact, it is said that she was given this data by her professor just to keep her silent. But I don't know the fact about it. But the truth is, she worked on huge volumes of data for several years. You must remember that it was done in 1868 when there was no computer, there was no calculator. She had to do it with hand. And she did it so meticulously that she published the evidence of a luminosity period relationship in this particular type of stars, which enable Hubble to discover that the universe is expanding. So these Cepheid variables, these are called the light curves, meaning that this x-axis is the time axis, and this is the magnitude. So as you can see, the brightness of the star varies with time, and it varies in different ways depending upon different stars. But what she found is that its speed is directly related. Its speed is directly related to the, in fact, the logarithm of the period. This is on the log scale. The logarithm of the period is directly related to the absolute magnitude of the particular star. So absolute magnitude, I hope many of you might be aware of it. If you are not aware, absolute magnitude is the real magnitude of the star when it is kept at a fixed distance from us. And apparent magnitude is the magnitude or the brightness that we observe. And this magnitude scales all these things. I do not want to go into the details. I assume that you know.
Sajeeth?
Yes.
It may be useful to just mention that magnitude is just negative logarithm of luminosity.
Okay. Okay. You have already mentioned it. So there are several jargons that I am using, which I did not go into the detail because I did not want to repeat it to those who know it. But just as what Seth was mentioning, this magnitude is the negative logarithm of the, in fact, the flux. Flux is the amount of light that is coming. So which means that the larger the magnitude, the fainter the object is. That is an important point. So if you say that an object is at the 20th magnitude, it is too faint for you to see. If the object is at the 12th magnitude, it is very bright. So that way, and some of the objects like the sun, for example, is in the negative value, which means that it is too bright to be photographed even. So those are the just some of the jargons that are always used. So the only thing I want to mention here is that when the magnitude becomes larger, the fainter will be the object. And it is, in fact, the negative logarithm, as Sash was mentioning, of the flux of the particular object. Okay, now let us come back to Aladdin. And this is, as we have seen, this is the default screen. So first thing we do is that we type in M31 here, which is the command window. And in that we type in that we want M31. And when we do that and we select the particular band, which is a pan-stars band, we take the pan-stars band. And this is done just the way we did earlier. And then we open Topcat. So we have Topcat also. And what we do is that in Topcat, there are different options here. And we go to the Virtual Observatory option, which is a VM menu here. So in the Virtual Observatory option, you will find that there are options for cone searches, which means that you can take a region of the sky and observe them. But we are interested mostly in the catalog service for this particular problem, because we want the catalog. We want to know the period of the particular stars we are looking at. We are not interested in seeing the objects. We are interested in seeing the catalog of the objects, which is related to the data that has been produced by astronomers after doing long time observations on these objects. So we take this particular Vizier catalog service from it. And when you click on that, you will get a window like this. So this goes to the Starsberg.fr France web server, Vizier server. And in that, there is option for count selection, which is the option that we saw here. Also, we have options for all rows, which means that we can have the entire rows in that particular table for our studies. And there is option for selecting by category, by keywords, survey, missions, etc. We are interested in variable stars, and we are interested specifically in Cepheid variables. So we'll go for this keyword option, and we will select all rows from this and the keyword option, so that we'll be able to enter the particular catalog we are interested in, which is the M31 Cepheid variables, which means that we would be looking at Cepheid variables in the direction in the field of view of M31. The problem in astronomy is that distance is to be estimated, either we're using redshift or with some other parallax method or something. So we can only say that when we see a set of stars, some of them may be from our own host galaxy, Milky Way, or some of them may be part of the object that we're looking at. So there is some possibility that we may end up with erroneous data, because the stars we are expecting to be, say, on the surface of the particular Andromeda galaxy may not be on the surface. But that is accepted, and we can easily find out them in one way or other, separate them in one way or other to get a better estimate. So this for this particular catalog, I'm looking in Sinbad for M31, which is the galaxy, the Andromeda galaxy, which I'm interested in, and also for Cepheid variables that are found around it. So when I click that, I get a long list of different tables. In fact, each of these tables is associated with the popularity. Popularity is a significant thing, because that mentions how many people have gone through this data. And the more the number of people who have gone through that data, the better is the likelihood that the data is good, because people would find out if there are problems. So it is a good practice to go to those with highest probability, highest popularity, at least in the initial level. Because if you go, it's just like some brand names. If you keep on following brand names, assuming that they would be good, then their brand values will go high. Likewise, the moment you start going after popular surveys, their popularity increases, and that may create wrong conclusions. But I am just suggesting it at the starter level. It is good to take one of these popular surveys and try to analyze. So we have different options here, and each of them is representing a paper that is related to it. And we have, of course, the descriptions are also given, which says which are the latest ones. For example, 2018 is here, which is one of the latest optical and IR surveys, and this is done on variable stars. So let us select this one, but for example, and when I click on that, it will open up in Topcat like this. So it is showing me different tables from the same paper. So these are done in near infrared, optical, likewise, and different observations that they have done. Each of them is there. So in this particular data set that I have taken, there are about 462 CFIT variables that are available here. And what I want to do is I want to plot it on top of Aladdin to see how Aladdin to see where they are located. So Aladdin and this Topcat can easily communicate with each other. And as you can see here, this indicates that Aladdin is already linked or connected to this particular Topcat version, which means that Aladdin, a Topcat can directly send data to Aladdin. And that is what is made possible by the interop facility that is available in Topcat. So when I do that, before I do that, I'll just open my Aladdin and insert the Andromeda Galaxy to my screen, so that when I click interop, I'll be able to send data to this. Now, when I click the interop option in Topcat, just to send data, I find that these data points come up on my screen. So immediately these data points are there on my screen, and I can now I also get a list of these objects. So each of these boxes, when I go to them, they will start blinking, and the corresponding objects, when I move on this table, the corresponding object here will start blinking, so that I can, if I want, I can select some of the objects and discard some which are not to be included. In fact, by moving my mouse, by clicking the left button, if I drag my mouse, these objects get selected, and that's how this table gets displayed on the screen.
Sajeeth, I have a question.
Yes.
See, you are, I just missed something in between. You are actually saying, which kind of objects, and you are displaying them.
Yes.
Right. Now, can I do the reverse? Can I have a questionnaire in which I say, I want stars with this property, and then it says.
Yes, absolutely. You can get that. Because
that will be the realistic way I do the observation.
Yeah. Yes. In Simbad, you can specify what kind of objects you want. For example, okay. Here I said I want CFIT variables. So likewise, you can say, if you are interested in AGN, you can say I am interested in AGN in this particular region of the sky, which I am observing. And I want to find out what are the objects that are there in this region of the sky that I am observing, because I am seeing something particular there. I want to know what it is. Then you can, of course, use Simbad and Topcat to do that and display that object.
Okay.
Can I ask a question on the same line?
Yes, please.
Is it only for larger bodies, or is there a way to identify molecules which are there in that region?
Oh, no. Molecular level, it is really difficult to keep data, and I'm not sure whether there is any data on the atmosphere. People have been trying to find out the details of the atmosphere by looking at the light that is passing through them and analyzing, taking the spectra, for example. Those are archived, but I'm not sure whether Simbad has that data. But of course, these are all archived, and they should be available.
Thank you.
Sajeeth, just one thing. Yeah. So what Madhurima was asking, that is the kind of thing which I was actually originally asking. What I'm saying is, can I put a query saying that I want objects which have an absorption line at this wavelength and then get them?
It won't be that easy here because
Okay.
what you will have to say, it will be possible if somebody has made a study on that.
Okay.
Because all these things are done with the help of metadata. Metadata is data about data. So
I agree.
what Aladdin and what Simbad, for example, does is it divides your paper into different regions, find out keywords in it, and keeps tag of them. So whenever you make a query, if you are saying hydrogen emission, that may be easily found. For example, because many people have worked on that. Or, yeah. So likewise, but if you are asking for calcium at a particular wavelength, a redshift or something like that, I'm not sure whether that would be that precision we have.
That is probably the original contribution one can do towards this.
That's right. That's right.
Okay.
Shall we go on?
Yes,
yeah.
Yeah. Okay. So what I have been trying to say is that you, now by selecting these objects, you are able to find out the details, the RADEC values, which are the coordinate values in the sky, their period, and also their magnitudes. These are the J magnitudes, for example, one of the magnitudes. So what we want for finding out the distance to this object is we are going to apply the period luminosity relationship. So we want the absolute magnitude and also the period. Period we already have as P in this data set. And the apparent magnitude, the observed magnitude is here. And we can, of course, because of the period relationship, we can, of course, use this information to find out the absolute magnitude of the particular star we are looking at. So for each of this object, it will be possible for us to, okay, we have the period and also the magnitude of the object. And for each of this object, we'll be able to apply the period relationship, the period luminosity relationship to estimate the absolute magnitude. And for that, we'll be using this formula, which is directly from the formula that we mentioned earlier, which was given by Miss Levitt for the period relationship. So in fact, what I get as output here will be the absolute magnitude. So I have just modified that. Of course, when we do this calculation, we won't be using this error value of 0.1 just because this is a plus or minus 1, which is the error bar that we expect for our data set. Now, what I'll do is that I have got the period, I have got the apparent magnitude. Now I want to calculate the absolute magnitude. For that, what I need is an additional column. I can easily create the additional column by right-clicking on this particular table that appears below the Aladdin screen and selecting add a new column option. When I click add a new column option, it will display this particular screen. So I have to give a name for my column, which I give as M, representing the absolute magnitude. I have the apparent magnitude and now I want the absolute magnitude. So I'll just insert the formula there, which is related to the period, and I can get the absolute magnitude by just inserting the column. So when I do that, it tells me that it has successfully created the column and I get the absolute magnitude corresponding to each of these objects. So J magnitude is its apparent magnitude, and now I got the absolute magnitude of the particular object. Once I get the absolute magnitude of the particular object, I can find the distance to that object by using this formula, which also can be derived from the 1 by r square relationship that we know for electromagnetic signal. What is 1 by r square distance? As the distance increases, the inverse square law that is what is applied to to be applied to get the observed magnitude. So I know that this is absolute magnitude. I am observing this particular star with the apparent magnitude, which is represented by this J mag here, and this is the absolute magnitude. then I can just insert it into my magnitude relation, the magnitude relationship that of which Sej was mentioning it before. If I put it in there, I can get the equation for the distance to that particular object. And I shall surely give you some links to these tutorials, how these are derived and things like that, although I do not want to go into the details here. That will tell you what the distance is. So what I need to do now is I have this formula. So I need to introduce a new column into my data set just as before by right clicking. And doing that, I find that I get the distance to Andromeda as these values, which is just shown by this histogram. It ranges from about 1.2 million light years to something like 2.27 million light years. So that is the distance I obtained. Whereas, so these are the objects that I was using, and many of the objects are not on the galaxy, it's outside the galaxy. Some of them may be misleading. That could be one reason, because the exact value expected is something like 2.25 or 2.5, I think 2.5 million light years from us. So that difference is mostly because one of the reasons is that we have been biased by the selection of the particular objects which were linked just to one region of the Andromeda galaxy. We were not considering anything from the center or from the other side, which could be the reason for the case. But
Sajeeth?
Yes.
Yeah, I wanted to ask one thing. Probably you will be coming to it, I don't know. See, in addition to the 1 by r square, there will be some changes because of local absorption and so on. Does this take care of the local environment?
Yes, that is the corrections that we apply. In fact,
Okay.
we'll be applying corrections to the data, and most of the data that we have used here are corrected for those
Corrected ones. Okay.
Correct. So those things are taken. That is one of the advantages of using these catalogs, because most of the observational corrections
processing has been
already has been applied.
Yeah.
So the actual value you are expecting is something like 2.54 million light years, whereas what you get here is much less than that. I was trying to explain why it was, mostly because we have been biased by the particular region. We have missed out everything beyond this particular region. Maybe that's closer to us, and the galaxy itself is extending to some few hundred light years. So that may be one reason. Then there may be some of these objects which are here may not be on the galaxy, may not be part of the galaxy, maybe in between or somewhere. And also we have neglected that 0.1 factor, which was the error bar that was in the formula itself. So that all might have contributed, but nevertheless, it is a good value because you are seeing almost a normal distribution here for the values. So it's not systematically biased by any of these. So I would recommend you, before I conclude, I would recommend you to go to this particular tutorial on both Topcat and Aladdin. It's a very useful tutorial describing the whole flexibility in a very brief time of about 1 hour or even less than that. And it would be useful to take a look at. I think that gives you a very quick and maybe dirty introduction to the capabilities of these tools, but I'll be open to take questions and definitely like to know whether I could communicate it. Thank you.
Very nice, Sajeeth.
Yeah, thank you.
Questions in the chat, maybe we can start looking. So there is a question. Shall I post it to you on the chat?
Yeah, please. Yeah.
Okay, so that's first, and there are a couple from the YouTube which I'll.
Ma'am, shall I read the questions?
Yeah, please. That would be easier. Yeah.
Okay. Go ahead, Devika.
Yeah. Sir, thank you for the wonderful talk. First of all, I will read some of the questions from the YouTube.
Yeah.
Kyle Purs has asked, how can I access this database? He might be wondering whether this database is free or not.
It is free. It is absolutely free. And the links that I provided, you can just Google for Sinbad, for example, or for ESO. For example, if you are looking for sun-related data, Soho is a very good site. Then there is the Sloan Detailed Sky Survey, SDSS, which has a lot of tutorials on how to access data, how to write queries, how to write SQL queries, for example. All these things are available in SDSS. SDSS is a very good site. I just missed in the talk, but you should not miss out. That is also a very good site. You should go and take a look at it.
You mean the Sky Survey?
Yes, Sloan Detailed Sky Survey, SDSS.
Yeah.
Okay, sir. Then there is another question by Hank. He's asking, does this database tell you which planet is the biggest? Here, he might be wondering whether these databases have data about planets or maybe exoplanets.
Yes, there is data about planets, exoplanets. All these things are available in the database.
Okay, sir. Then I have one question, which is NED and Visio, is it different from Sinbad, or is one database preferred over the other?
Hey, this is a contributory system. The whole Virtual Observatory Alliance is there, which India is also a partner, and India has developed several tools. France has developed several tools. ESO, for example, the European Union has developed several tools. NED, the NASA's exoplanetary database, NED is also there. So all these things are linked together, and one can move from one to another. There is no restriction in the way in which they can be accessed. And that is the advantage of using Virtual Observatory.
Okay, sir. So does this serve the same purpose, and is one more advantageous than the other?
No, all of them have data which they are more using, or they have focused in different areas. Many of the databases may have, if you are asking, redundant data, but that is natural because when people collect things, there will be redundant data. But all of them are linked in such a way that if you want to access a particular object, you can always get distinct catalogs on them. It would say this is outdated. You can see when you make a search, you can see that some of the data it would say it's obsolete, meaning that something else has come up which is more accurate than that. So all these things are in the data itself, but nobody deletes any of this data. So even if it goes obsolete, it is kept, it is stored there, so that maybe after some time somebody wants to look there and they may find something useful. So if you are asking whether any of this is superior to other, I don't know whether there is any direct means to answer that question, because it depends upon what you are looking at, and yeah, it depends upon what you are looking at.
Okay, sir, I understand. Thank you. I guess there are no more questions.
Can I ask one question? Hello.
Yes, please.
It's a bit of a technical thing. So I'm not sure if everybody in the audience will appreciate. See, when I am having two catalogs, and in say catalog A and catalog B, and they describe the same system, that is when there is redundancy. Now, clearly, you will not have an exact, point by point match when you are doing this. There has to be a certain tolerance saying that if this point is within this angle, I identify it as the same object. What is the tolerance which is usually used?
The tolerance is to be decided by the astronomer himself or whoever using the data.
Oh, I see. So this will just give a place. Okay. The patch. Okay.
So I have an option to say what tolerance I am allowing. For example, when I plot the galaxy, it just knows the location of the galaxy. Then I have to say how many degrees I want it. The default is some 40 degrees or something like that. You can adjust it. You can zoom in, zoom out, and you can
Okay.
Sir, can we take one more question?
Yeah, sure.
I think Yogesh has a question. He can
Please.
unmute himself.
Yeah, please.
Yogesh, you can unmute yourself and ask him directly.
Yeah, you can see the question in the chat, but it doesn't seem very clear. I mean, at least I don't understand the question. So,
Ma'am, audible now, ma'am?
yeah, could you be a little louder? We can hear you now.
Ma'am, yes, ma'am.
Yogesh, we can't hear you.
I'm still.
It's better. Can you hear Sajeeth?
So I
can see his question. Have you ever have trained a cluster computer with a neural network instead of deep learning, deep feedback simulation of real condition with trial and error method with various algorithms to optimize, just like bragging and boosting, and look out at sky for finding new or important of previous to
so shall I continue
further, not just limited. Yeah, okay.
Yeah. Actually, my question was: have you ever trained a cluster of computers with instead of just algorithm to solve and equipped with neural networks instead of deep learning or data feedback? Instead of that, we can give a simulation of real conditions, learning with trial and error method, like similar way to human thinking, and with various algorithm to optimize as usual, cause no methods is efficient. And look at the sky for finding new things or important things or worth to note things. So because many astronomers are looking at the bare sky for years, and later they're finding a worthwhile discovery. So, but instead of that, if we spend time on these computing resources, we will be having a time to explore a time in other domains of research, like one of not just included to the united force or gravitation, gravity on mystery, like that.
Yes, there is simulation. That is what you mean, isn't it? Simulation is done in many cases where we do not have access to the data. For example, what happened after the 5 minutes or 3 minutes of the inflation? We do not have data for that. For how the galaxies evolved, or how the planets evolved, or how the stars evolved, we do not have data for that. In such situation, we have to rely on some mathematical models, and based on that, we always have simulations, and we can run the simulation at high speed so that we'll be able to see this long time evolution in a very brief time. So that is where we apply simulation. But in other cases, most of the astronomy is trying to do is to understand what is there, rather than trying to predict what is there. Of course, we'll have predictions. We'll realize that there should be something there. For example, in the case of M87, which I mentioned, when people saw this spot in the radio, they realized that there should be something there. So that is when they all went there and looked at it in detail and discovered that there is a big jet that is coming out of it. So all these things, of course, are see, even now, even after having all this scientific development, we have to admit that we are yet to understand this universe and its complexity. We are trying to understand it, and that is where observations are required, and that is why astronomers are spending a lot of time trying to find out how these things are happening. And that's why we are moving to gravitational wave astronomy, where we are trying to have an additional arm or additional dimension to see and understand these objects. But for things that we have models, what we try to do is we simulate them and we compare them with what we observe. for example, galaxy merges. We know that Andromeda galaxy is falling on us, or we are falling on Andromeda, because Andromeda is a bigger galaxy. Of course, we may be falling on Andromeda, and this may happen in let's say 10 million years. And what will happen at that time, we can simulate, and we can say that this whole system may turn into a giant elliptical galaxy instead of the spiral arms and all this. In other words, so there are bars in the center of the galaxies. Our Milky Way galaxy itself has bars in its center. We know theoretically that these bars can be formed only if there are mergers. And that means our own galaxy have a history of different mergers that happened in the past. So all these things for which we need both the observation and the theoretical model we make out of it for doing the analysis. But simulation alone won't do. Simulation alone won't do, because simulation can be, the only criteria for simulation is that it should be mathematically or logically viable or logically acceptable. But that does not mean that it should happen. Recently, you might have come to hear about the greater revolution that this deep learning machines did. This, what was that? This protein folding efficiency. See, proteins can fold in thousands of different ways, and finding out how it may fold was it's still not understood. Even if we have machines today that are able to fold the protein in a particular way, we do not know why it is happening like that. We have observed that it's happening like that, and we have made machines to behave like that. That's all we can say about it. So this kind of understanding or this kind of models are built on observations, and these observations are definitely required to make models or to make theoretical conclusions and to create all these different simulations on computers. We cannot start a computer with some random initial condition and say that this is how it evolves, and so that should be the way in which the universe has evolved. We need to have different checkpoints in between where we will be able to verify that this is exactly what is seen here. And for example, simulation, we now very clearly know how simulation happens. So, sorry, this merger happens. I'm sorry. We very clearly know how merger of galaxies happen, and in what angle, what type of galaxies come, what kind of outcome it will produce, we know. Although we have not seen that, we have evidences for the outcome, and that is how these things are done. So I'm not sure whether I have answered your question, but of course, these experiments have to go and find out target values which have to be supported by the theoretical models.
Can I add one thing?
Yes, please.
Yeah. So basically, the way I look at it is a simulation is a substitute of solving a complex differential equation. What differential equation has to be solved and what initial condition has to be given has to be our ingenuity.
Absolutely. You're right.
Okay, sir, I think that answers his question. I want to know whether are there any more doubts?
Sorry for my interruption, sir. Hello.
Yes.
Sir, I wish to know that also instead of simulation, I'm talking about automation, sir. Automation of observing the skies. Like there are terabytes of, there are zettabytes of data, like in CERN laboratory. Humans cannot alone efficiently analyze the data and find about a new particle like X19, the boson, and other things. So that observational things can be done by automation also, right? Instead of simulating is where our creativeness end actually. Yeah. And we can focus on two areas where human intervention is needed, like observing a black hole or observing something a star merger can be done by automation also.
Yes, in fact, automation is done in almost all these surveys. I told you about this slow and detailed sky survey. It is observing the night throughout for more than 15 years now. Every night they are observing the sky. So they are constantly observing it, and this is all automated, and the data arrives. There is also another, I talked about the variable sky, variable stars, and all those things. There is something like the Catalina real-time survey, which is at Caltech in the US. They are observing the sky every night. They are looking for transients. Transients means those objects which suddenly appear in the sky and disappear. Like, for example, a supernova explosion or something like that. And all these things are linked with telegramic messages, meaning that once you observe something that is of interest, a telegram is sent to all the astronomers so that all the telescopes will start looking at that direction, and also all the astronomers will go and look at it. So this kind of things are automated, completely automated. And most of the surveys, most of the observations are automated because that is the only way in which this can be done. But there are also dedicated times which are allotted to different specific studies that are of interest. For example, all these telescopes allow you to do dedicated observations, not the surveys, but dedicated telescopes are there. GMRT, the Giant Meter Wave Telescope, radio telescope we have in India, that is being used for specific, you have to make a request to them, you have to make, specify your science goal, and then only you will be allotted time, because there is a lot of demand for it. So there are both these things. Automated surveys are there, which do overnight, daily, monthly, yearly studies, and all of them are archived. And most of these bigger surveys which are planned are all automated, and they take the pictures, and except at specific situations when some rare event happens, they will be given specific assignments. Otherwise, it's all automated.
So what about interpretation and analyzing the data? Like computation can easily find anomalies and any other things.
Yes, those things are also automated. There are pipelines which are written. They are called pipelines.
Can I call you back in 10 minutes because I'm in the middle of a meeting? I'll call you back.
Because there are pipelines which are written, which are programs which allows you to, in fact, get these things done in an automated manner. So all the data is processed automatically, they are stored automatically, and when you retrieve them, you get all the details. There are log tables which tells you how this process has been done, so that you can go back and correct them if that is also. Those things are taken care. Did I answer you?
Devika?
Yes, ma'am.
Yeah.
I think he might have some network problem. You have explained it well. Thank you so much, sir, for introducing us to this databases. It was very informative.
Yeah.
Sage, anything about future plans on this or later?
Yeah, I was actually talking to Sajeeth about the possibility of having student projects and so on, which probably in course of time one can think about.
Yes, of course.
And what about a longer workshop?
Yeah, so Sajeeth, one of the things which we were thinking was if we can have a kind of a workshop where, okay, maybe I'm a bit vague about it, but it's a kind of a hands-on session for people to learn.
Yes, there should be a small number of interested students, say a maximum of 30 students or something. We can, of course, organize a workshop, and we can see. I was going through many things.
Achha, Sajeeth, then I'll be one of the students. Okay.
Let's make it 33 so that we are not fighting for the seat.
Okay. Yes, Sajeeth. Yeah.
No, so all that I'm trying to say is we have plans for future, and we'll work this out.
Yes.
This is just the beginning of to be using artificial intelligence and algorithms and everything in astrophysics. It's supposed to be an introductory talk.
Yeah, sure.
Thank you very much for readily agreeing for this talk, and thanks,
Sajeeth, just one thing.
Yes.
Since you have been guiding so many projects and you are on to many such things, is there some website you keep where you upload these things and so on? That would be a very good thing for people.
I agree, but the problem is
too much of work.
Actually,
I agree.
Yeah.
Yes.
I would like to do those things, but
best is
I
if we
have
have
only two hands. Yeah, I have only two hands and one head. Yeah.
If you have a workshop, then this can be work assigned to some people who are enthusiastic.
Oh, sure, definitely.
Yeah. Good. Nice.
Yeah. So if there are no further questions, thank you all, and thank you all. Thanks a lot for readily agreeing, and Sesh, as usual, for.
Thank you very much.
Thanks a lot. Bye.
Bye.
Bye.